Okay, so yesterday we discussed Yukawa's theory, and today we're going to have part 2 of the discussion. So what was the theory? Well, the theory had our nucleons and antinucleons being described by a Dirac spinor, and they interact through a particle, or making use of a particle that we're calling a meson, which is just a real scalar with some mass. And the way they interact is the following. Okay? Very good. So yesterday, we talked about the propagator. Before, when we had our pseudo-theory of nucleons, where the nucleons were complex scalars, we denoted the real scalar propagator with a dashed line, and it's just a standard Klein-Gordon propagator. Okay? Now we have a fancier object to describe our nucleons, and we have a propagator that looks like I k slash plus m. It has two indices a and b over k squared. Sorry, this m is the capital M. There is an in. There is an identity matrix there. As I told you yesterday, nobody writes it, but we will. Sometimes, if I remember. Okay. Divide by k squared minus m squared plus I epsilon. And this is something that propagates a nucleon from B of type B, something of type A. Okay, and this is the arrow, and we're going to have momentum k. Okay, and the interaction vertex, well, that's a propagator. You know, I wonder if I should be going in that direction.
We use the other convention. We use from A to B.
You mean this? This was BA.
Is it symmetric?
No, it's not symmetric.
So
what you mean? What you mean is that before we had yesterday we had a B and an A.
Yeah, for that diagram, yes, for that diagram.
I see. Yeah, well, but this is the one that we should have used then. So yesterday it wasn't. Maybe I didn't actually write it correctly.
So your convention is that contraction of side-to-side dagger is
That's right. Yes. So psi annihilates a nucleon, right? So we should have the B according to this, and then the A is a propagator to this point A, to this point 1. I mean, in coordinate space. If you do it in coordinate space carefully, you will find that this is a correct convention. I mean, that this is a correct ordering of the indices. Okay. All right, very good. So we have the interaction. The interaction was simply minus Ig delta AB, and we had a nucleon and an antinucleon. Here it doesn't really matter because this is symmetric, A and B. Okay? And we said that we were missing one piece to complete the Feynman diagrams to actually start doing calculations with this. So what were we missing? Do you remember? Yeah, rules. For external nucleons. And antinucleons. Okay? So yesterday we also said that we were going to use exactly the same trick as we used for the photons, and that the two important formulas that we had to remember were the following. If we have this, matrix with indices A and B, this is equal to the sum over the two possibilities for U. So we have K index A, U bar S index B, K. Okay. And we had a similar formula for the wave functions B. Okay. So the idea was to use exactly this in order to learn what the missing final rules were. Okay. So what we're going to do is our usual experiment where we create particles in our accelerator and we detect them somewhere else after they interact. They are going to interact somewhere here. They are being produced by some scattering process. And they are being measured by some scattering process too. And the kind of particles that I'm going to tune my detectors to measure and that I'm going to tune my beams or my generators of the beams to produce would be a nucleon here. And here I want to detect a nucleon. And here I'm going to produce an antinucleon. And here I'm going to detect an antinucleon. Okay? So the standard convention so far, which is not particularly nice, but we have been using it so much that I can even remember. So this is K1 and this is K2. This has been our convention for incoming particles momenta and outgoing particle momenta. Okay. So once we have this, we know from the LSZ formula, we know from unitarity, that this scattering amplitude, the big scattering amplitude, will have 4 poles, and the 4 poles will correspond to propagators. Okay? Now, when we are very, very close to producing on-shell particles, those 4 poles will blow up, and LSZ tells us to remove them and just keep what is left. Okay? And then the amplitude would be whatever is left here, and we will also have amplitudes here which are not interesting for us. Okay? So if we look in this case, the propagator, say, the propagator is going to look like PA slash plus M over PA squared minus M squared plus I epsilon. Okay? Now, when we look at the propagator, and we look at this formula, and you look at the definition of the propagator, what do you think is the wave function that I have to put in for an incoming nucleon? So maybe we can do it here. So what I'm going to do is to use the same trick that I used there. We have AB, and now we're going to write this as the sum of UA, UB over PA squared minus M squared plus I epsilon. Now, LSZ, they tell us to remove let's use red. They tell us to remove this part. We keep this one, okay? And now we see that on one side, we're going to get the A index, and on the other side, we're going to get the B index. So with this amplitude, which is a nucleon that is outgoing, I have to associate this part, and with the nucleon that is incoming into this particle, we're going to associate this guy. Okay? So let's actually write it here and keep it here. So that might be actually convenient. That must be a sign that we're doing something right. Or something wrong. One of the two. So is that clear, what I'm doing here? Okay? These guys are going to be the wave functions, or here of A, of the particle that is incoming, and B would be of the particle that was outgoing from this process. Okay? And we have to sum over both, because this is a quantum mechanical process, and we had probability of producing both. So if we want an experiment where we only have one kind of a spin, 1 or 2, what do we have to put here? As we did with the photon, we put some polarizer. Okay? But if we don't have to worry about that, well, I mean, we could do it. We can put a polarizer, and then we will project out one of these two guys. But in our thought experiment, we are thinking about everything that can happen in this interaction process. That is a yellow one. And we're looking deep inside what is happening once we tune the external momenta to do, or to have as the most important contribution, this process that I'm drawing here. Okay? So, as I said, this guy will then be identified with a particle that is incoming, and this guy will be identified with a particle that is outgoing. So what are the rules? So if we have an incoming nucleon, we will multiply by U. If we have an outgoing nucleon, we will have this guy. Okay. Now we're going to do exactly the same thing for these ones. Okay. Now we realize that here the propagators will have a minus sign. Okay. And therefore, we're just going to get that an incoming. So now we're going to use this part for these guys. And we're going to get that for an incoming antinucleon, we should use V bar. And for an outgoing antinucleon, we should use V. Okay? Yes?
Why aren't we off by an overall minus sign? Because the propagator, if we set k slash is minus k, and then
the minus sign is irrelevant, right? We're going to be computing the magnitude of this object. So this was just a way to get what this object had to be, okay? But the overall minus sign is not important. This is M, right? This whole object is our M. Okay.
I guess there's no way this diagram could interfere with other diagrams. No.
Well, you see, the minus sign is overall for all these sums, okay? And these are the only sums that can interfere, right? Okay, very good. So imagine, as we did some time ago, that we consider, this is really handy, huh? Oh, very smart. Okay. Very good. So now, let's do some examples. Imagine that we are scattering, say, a nucleon and an antinucleon, and producing another nucleon and an antinucleon. Okay? So what are the Feynman diagrams I have to draw? well, I'll get something that looks like this. Here is PA, this is PB, here is K1, here is K2, and there will be another one which can look like this. This will be PA, this will be K1, and this will be PB, and this is K2. Okay? So we could write down what each of these diagrams gives, but instead of doing that, I'll leave you this particular one as an exercise. And we're going to do another one, which actually reveals something much more interesting. This is the one we're going to do. Nucleon-nucleon scattering. Okay. So where are the Feynman diagrams for this one? Well, the Feynman diagrams are, we have something like this. Okay. PA, PB, and then K1 and K2. And we have another one, which is this one. But here we can have now K2 and we can have K1. So we can have nucleon 2 here and nucleon 1 here, nucleon 1 and nucleon 2. So let me compute the first one for you. So this is going to be the first example of actually computing Feynman diagrams that contain fermions. So the way I like to do it is the following. It's actually kind of strange how you have to write it, but I find it the simplest actually. I prefer to start always to pick a fermion line, and then I start where the line actually tells me to start. So it tells me to start here, okay? And then follow the whole fermion line. The drawback with following the fermion line in the natural way is that actually when you write down the answer, you have to write it from right to left, okay? But well, I mean, that's not that terrible. So let's actually do it. So you will see why we have to write it from right to left. Here is so simple that we could have done it immediately without actually following the line. But let me do it because later on we will do more complicated examples. So I'm going to follow the line. So here is another rule. I mean, it's a suggestion, really. So follow each fermion line. And write from right to left. Okay? So what do? We pick one of the two fermion lines, say the top one. So pick the top in this diagram. So pick the top line. So we follow the line. We start with PA here. And what do we write according to the rules? Well, we had the rules right there. So this is an incoming nucleon, so we should put a U. Okay? It's on spin SA. Okay? And now we follow the line, and we have an outgoing nucleon. Okay? So what are we supposed to use? A U bar. Okay? But my rule tells me to write from right to left. So I'm on the right, I'm going to write to the left. And isn't this nice? This is a number, right? So that's part of my contribution to this Feynman diagram. Well, the rule tells me do that for every fermion line that you see in the diagram. There is another fermion line, right? The bottom one. So the bottom one will give me exactly the same thing. So I'm supposed to start from this side and then to SAB, and then PB, and we write U bar of S2, and then we have K2. Now I'm done with the fermion lines, so I can go back to my original Feynman rules and say, well, for every interaction vertex, I put a minus IG, okay? You see that my Feynman rules had the delta AB, but they are doing exactly this contraction the way I'm doing it. Yes?
However, the propagators that you have, well, this is just a scale propagator.
Yes. We will see with the other propagators. Just stick with them. So these are even faster rules than the ones we have there. We could do it following exactly the contractions of the indices, okay? But somehow I'm now skipping the contraction of the indices, so I'm not using this delta AB. I'm telling you a rule where you can skip that and now replace each interaction vertex by simply minus IG, okay? And this is what you're going to find in books, okay? In the books, people don't write the delta AB that I wrote there because they will tell you about this rule of doing things faster by writing. Well, they don't tell you to write from right to left. But, okay? What am I missing? Am I missing anything in the contribution? There is a propagator, and the propagator is I over PA minus K1 squared minus M squared plus I epsilon, because this was the meson, okay? Now you can do the same thing for the second diagram, right? And the second diagram, all I have to do is to change K2 yes. PB. This is diagram.
Extra information that I should have in order to compute these amplitudes.
What's the other information that you need?
The S1 and S2.
Yes, that's right. So just like for photons, when we talk about a nucleon, okay? So of course, in our thought experiment, we were summing over both. But if we put a polarizer, then we will project out one of the two possibilities, and we will be left with only one. So you're right. So we should give here SA, SB, S1, and S2. We should also give that data, which I'm using already here, but we should give it. So we now have PA K2 squared minus M squared plus I epsilon. But there is still something funny about this formula, which is the following. This diagram looks like the diagram that I would naturally draw for this process, where the wave function of the outgoing states is actually this wave function. This diagram looks like the diagram that I would get if I had the same incoming particles, but the wave function for the outgoing particles, what do I have to do to it? It seems that I have to swap them. But these guys are fermions. So if I swap them to make this natural, I would produce a minus sign. So in fact, we're supposed to put a minus sign here. And this is a relative minus sign. Okay? The overall sign is not important. The important thing is that there is a relative minus sign between the two diagrams. Okay? Now you can see what the rule in general is. If you have many, many fermion lines, okay, so you can draw all of them. You can imagine that the first set is fixed, and in the second set, you fix one, you make one choice, whatever choice you prefer, and then you compare the other diagrams with respect to that diagram, and if the permutation is even, you put a plus sign. If the permutation is odd, you put a minus sign. Okay? Now, the reason I drew the first example was not just to waste time, because clearly we don't have too much time. It was because I want you to check that with that minus sign, in this case, if you put this together with the other case, you can check crossing. Okay? Very good. Okay, so let me give another example because Andres was asking for it. So we have to actually, it was a good idea. So this is going to be an example of a Feynman diagram, not an example of an amplitude, okay? So we're going to do an example now. Okay? And what is the Feynman diagram we're going to consider? It's a diagram where you have the interaction of a nucleon. It contributes to the interaction of a nucleon with a meson, actually with two mesons, which goes into a meson and another nucleon. Okay? We're going to draw one diagram that contributes to that. So we're going to have the nucleon that is coming in with momentum P0, say. It interacts with our nucleon, with one of the two. Then it keeps going. It interacts with the other nucleon. It keeps going, produces our final nucleon, our final meson and the nucleon, which with momentum P3. Sorry? Yes. Oh, that's very important. The lines, the fermion lines, always have the same orientation. Because the vertices always have one line in and one line out. Okay, so it's impossible to have contradictory orientations in your diagram. So what is this going to be? Well, once again, I start following the fermion line. Actually, if for some reason you prefer to think about the interaction as happening from the right to the left, then you would actually write it in the way that is drawn. But I just prefer to write them from here to there. So I have to pay the price. So we start with this guy, and we write it on the right, okay? U of P0, of course, with some being a 0, say. Then what should I write here? Yes. So let me actually, to make this simpler, let's actually follow first the rules that I had here, okay? The rules that I had there actually had indices. Okay, so it had an index A, B, and C. The reason I'm putting a single index is because the delta function locks them together, okay? So if I have a UA, I have to put here the propagator, but I look there and see what is the propagator that I have to put, and it turns out to be I P1 slash plus M, so this is the nucleon, and then it has a BA over P1 squared minus M squared plus I epsilon. Okay? Next, I'm supposed to put this propagator, and the index B is contracted with this guy. So I get I P2. Note that I'm not bothering about writing P2 and P1 as the momentum of this guy plus the momentum of this guy. I'm just saying whatever the momentum of this is, P1 will be the sum of the two momenta. Okay, I'm not bothering to write that. That's trivial. If you want to do it, you can do it. But since we're not computing an actual amplitude, it's not very important. So we put an M here. Of course, there is an identity. And then we have what? We have CB over P2 squared minus M squared plus I epsilon. And then the last guy is our U bar C, P3 of SC. Okay? This, of course, is correct, but it doesn't look cool. And it's very important when you write things to write them in a nice, elegant way. So actually, we're going to write this in a much nicer way. We're going to write it as U P0 S0, okay? And then we're going to write I over P1 slash minus M times I over P2 slash minus M U bar of P3. Sorry, S3. Isn't that much better? I mean, you can show your friends, and then they will all be scared by what this means. But you all know what it means. Okay. Very good. So, at last, we're ready. Yes.
Can you repeat why you wrote it this way?
Which way?
How you wrote it like that?
How I wrote it like this? Well, now I'm thinking about this, right? This guy is a 4-component object. This is a matrix.
Oh, okay. So it's the inverse.
This is a matrix.
That we have before, right?
Sorry, this is the inverse. Yes, this is the notation for the inverse.
All right.
Right? So this thing is a matrix. This guy is another matrix, which are multiplying. And this guy is a row vector. Isn't that cool? I mean, looks much nicer than this. But that's the point. So you see, you show it to people. Once you understand it, you say, okay, now I know that I don't get confused. And then you show it to other people. Look at the calculation I'm doing. So cool. Yeah? But you know that this is all it means, right? And in indices, this is what it means.
What happens to the IX ones?
You see, we're working. Oh, you mean what happens to the I epsilons here? We're working at 3 level. I mean, this is called a 3 level because there are only 3s. So at 3 level, if you're working with genetic external momenta, this will never remotely be 0. Okay? And epsilon is an infinitesimal parameter. So most books and most reasonable people would never write the I epsilon in these formulas because this is never 0 for genetic scattering data. Okay? I keep writing it because I believe this I epsilon is important. Okay? But I'm not going to tell you why. Okay. So at last, we're ready to do spin or electrodynamics, or QED, or the theory of electrons, anti-electrons, and photons. These guys are also called positrons. Okay? So instead of talking about nucleons and anti-nucleons, we're going to be talking about electrons and anti-electrons. The great thing is that we get to keep the same Lagrangian. You just have to erase this. And what do we have to add to it? Well, we have to add our Maxwell Lagrangian plus some interaction. Which we have to find out. Okay? And that's what we're supposed to do. So what was the trick we used when we had the complex scalar field? We said that we want to find an interaction between A mu. So we need an interaction between A mu and our spinor fields. Okay? We want an interaction that has the smallest possible dimension of the coupling. Okay? So this object, of course, is a vector, or it transforms like, it has the same Lorentz transformations as the derivative operator. And we want to make something that is a Lorentz scalar. Yes?
I remember when we first wrote down the almost Maxwell Lagrangian, we had this other term, the that we needed.
Yes. So I'm writing now the true Lagrangian, right? And then when we want to use it, we will have to fix it.
Oh.
Yes. Okay. Well, but the Lorentz transformations of this, actually, if the index was up, it would be a vector. Since it's down, it transforms as a one form. Okay. So, which is the same transformation as this. And therefore, if we want to make something that is Lorentz invariant, what do we have to do? We want to have something that that contains the spinor fields psi and psi bar, such that we can put it together with this guy and get something that is a Lorentz invariant. Okay? So what kind of combination can we put together? Well, a hint comes from this term. You see that from all the construction we had in the past 2 days, we learned that this object was a Lorentz invariant, and that's why we had it in the Lagrangian, right? But now we know that this guy transforms on the Lorentz transformations just as this guy does. So what if we replace this exactly by this? Do we get a Lorentz invariant in that case? What do you think? Yes, so that looks like a reasonable choice. So let's put here in the interaction something proportional to that object. Let's even put it where it goes. Well, doesn't matter because you guys know that the A mu is not a matrix, so it can go anywhere in the formula. So maybe I can write it in several ways. So I hope you realize that this thing is the same as right? Because this guy is a matrix, and this guy are 4 component objects that are contracted with this matrix, multiplied with this matrix, but this A mu has nothing to do with those matrix operations, okay? What we get from these operations is also a 4 vector, okay? It has 4 components, and now once we have the 4 components, we contract it with this vector, okay? Now, what's our job? Our job is to find alpha, if there is any, such that we can decouple the unphysical modes, or we can make them redundant, the unphysical modes of our vector field, so that our Lagrangian has a chance of describing photons, which are only supposed to have 2 degrees of freedom. So we need a gauge redundancy or gauge invariance of the form the standard form. This is a standard form that we have. So what was the trick we used in the case of the complex scalar field? And the reason was that the complex scalar field already had a symmetry, right? Does this theory have a symmetry? So we're in luck. So very nicely, we didn't say yesterday, but our Dirac theory has a global symmetry. Given by sending our field each one of the 4 components, okay? All 4 components have to be rescaled by the same factor. Now, if you do that, obviously, this is invariant because this picks up a phase with the opposite sign, which cancels the one we get from here, so this is invariant. There is a global symmetry, and this implies that there is a current. And your exercise in Noether's theorem is to compute that current and show that the current is nothing but this up. Isn't that nice? Isn't this exactly the object that we are coupling to the gauge field? So somehow the gauge field is coupling to J, to a conserved current. So that's precisely one of the consistency conditions that we have to impose. Okay, and this is a general feature. Now, when we do this, we still have to fix, yes? Well, a consistency condition is that this guy has to be conserved. The reason is that when you write Maxwell's equations in the super fancy way of writing it with F mu nu, remember what the equations are, right? If you remember, the equations would be del mu F mu nu, and then you have your current. If you put another derivative, this vanishes trivially, so you need a conserved current. Okay? Okay, so let's do it. Well, let's put that piece together with the piece we already had. So what do we get? We get something that looks like psi bar. We can actually put the gamma here. In fact, I'm going to put it here. Okay, so we get I del mu plus alpha A mu times this plus a term, or minus, a term that is trivially invariant under anything we do. Okay? So I'm rewriting the Lagrangian plus the interaction term. Is that clear? So this is Dirac plus interaction. Dirac plus interaction looks like this. Now I can perform a gauge transformation, and the trick we used last time was to allow, or at the same time, perform a global transformation, which wasn't global anymore. What did we do? We allow theta to depend on space-time. So we do that, both things at the same time. So what happens? Well, from this side, so we get e to the minus I theta of x. In fact, I'm going to make an ansatz right away. My ansatz is going to be that the theta, just like in the scalar field, is proportional to this transformation. So I'm going to use a local transformation where theta of x is, just out of nowhere, just for convenience, I'm going to call the constant of proportionality minus e times the transformation that I'm enforcing on the gauge field. Okay? Very good. So if I do that, I get a plus sign, and then I get e w of x times gamma mu here, and then I get I del mu plus alpha a mu e to the minus I e w. Okay, so just one more step. and we should get something sensible. I hope. So what do we get? We get psi bar e to the I e w of x times, again, I forgot the gamma mu. Now, when this guy acts on this whole thing, it produces two terms. One when it acts on this, and one when it acts on the fermion. So when it acts on this guy, it produces something that looks like e to the minus I e w times, what do I get? I get e del mu w x, right? And of course, nobody told me, but there is something wrong in this equation. Exactly, yes, I haven't transformed A. And I told you we were doing both things at the same time. So somebody should have reminded me that I was supposed to do it to this guy too, and add here an alpha del mu w, okay? So we're doing both transformations at the same time. The transformation on psi with a local phase chosen for random reasons to be given by this, and a gauge transformation on A mu, which I'm doing right here. Okay? Very good. So if we do that, we get this term there. We get the original term acting on psi now. And the other ones don't really do much. They just go along for the ride. Okay? This nicely cancels with this. And now we need this to cancel that. And therefore, alpha has to be chosen to be minus e. If I do that, then this cancels with this. And I get something that is gauge invariant. So this implies is that a gauge invariant. Now by gauge transformation, I mean the composition or doing at the same time this local transformation on the Dirac spinor and on the gauge field. So if we put both things together, a gauge invariant Lagrangian is obtained as follows. So we have yeah, we can put the, let me put it here. Should I put the I inside or outside? I don't know. Minus E A mu. Of course, the trivial term so this is gauge invariant. Now, this combination looks very amusing. Let me actually pull out the I. So we get something that looks like del mu plus I E A mu. Okay? So have you guys ever seen something any theory where you had a standard derivative and then all of a sudden you had to change that derivative by adding a term corresponding to some connection in GR, right? Well, it turns out that there is a theory similar to that, but when you take your space-time and you endow every point in space-time with a Lie group, okay? And you consider at the same time on each point on space-time you consider vector spaces that are allowed to transform under that lead group, okay? Now, that whole combination of objects give you a big manifold. And that manifold can also have some interesting curvature. And therefore, if you want to define derivatives, you also have to define covariant derivatives, okay? Well, all that to say that this thing here is something that people like to call a covariant derivative, okay? So the long speech was just to tell you why people like to call this d mu. Okay, you will see this in many places. Now, it's a covariant derivative, but a covariant derivative for what field? Well, it's a covariant derivative for this field. And what is the nice property of this covariant derivative? Well, the nice property is that if you perform a gauge transformation, under a gauge transformation, the phase that this guy picks passes through the derivative, right? So under a gauge transformation, d mu psi goes into what? What do you think? Exactly. E to the, what was our choice? Minus okay? So it transforms covariantly under our gauge transformation, while the regular derivative did not.
Can you repeat the connection you made with like the covariant derivative with your idea?
Absolutely not, because it's completely outside of the scope of the course. It was only to tell you that people like to call this covariant derivative. Yeah. We can discuss it after the lecture if you want. I mean, if anyone wants to discuss that, that's a lot of fun. Okay. Oh, no, we don't want to erase this. This is really brilliant. Okay. Now we can write our Lagrangian in the super fancy form, right? That's all we had to do from the beginning. Isn't that insane? All that work just to put this slash. However, there is something important. The covariant derivative, just like in algebra, like in GR or in general in geometry, it depends on which object is acting, right? So it changes. Now you see here that there is this E. Okay? Our gauge field transforms always in the same way, right? But this E is telling us that the field we're using transforms in some representation of our group. Of course, here our group is kind of trivial. It's only a U1. So the only representations are classified by a complex number. And this complex number is called the charge. Okay? Now we can ask, just as an aside, I just remember, could this work? You remember all the work we did when we had the complex scalar? We had the complex scalar theory. And we did a lot of work to actually get something that was gauge invariant, right? And in fact, it was very complicated. It looked complicated. Could we just use this idea of making everything covariant and just get it to work? Well, this derivative is acting on this field, and this derivative is acting on this field. Now, what are the relative charges under the U1 global symmetry that this theory has? What kind of charge does this guy have with respect to this one? Do they have the same charge? No. One of them is a negative of the other one. So if we replace this by a covariant derivative, so what do we mean by this covariant derivative? So this we have to be del mu plus IE A mu, okay? So that should be what we use for this guy. And what should we use for this one? Exactly. Right? Because this is a different field, it transforms differently. So the covariant derivative has to be different, has to change. Now, of course, this is the dagger, or it is the conjugate of this whole thing. So people like to write this, and you will see it in your homework, that people like to write this as d mu phi. So the standard derivative acting on phi, now you put a dagger, and then you put d mu phi. Okay? Very good. So that was an aside. And the reason is that there is something like that in the homework. Actually, it's an optional question. As operators, but as fields, remember, this dagger is just a complex conjugate. In fact, I could have done everything. We are at the level of the Lagrangian, so this is a single complex object, right? And it's not a big object; it's just a single object, right? It's not like our Dirac spinor, which is a 4-component object. Okay, very good. So, what should we do? We now have our Lagrangian. So what's the next step? Well, the next step would be to quantize a theory, to write the coordinate space, Green's functions, write the momentum space, Green's functions, and from there derive Feynman rules using the LSZ formula to write down scattering matrices, okay? Are we gonna do that? No, of course not. By now, we should be able to guess what the Feynman rules are, okay? And start doing calculations. So Feynman rules. Okay, in the Lorentz gauge, and on top of using the Lorentz gauge, we're going to use the Feynman gauge. Okay. Well, that's a long way to say that if we see a photon line, what's the propagator we're going to use? That's right. It's going to be minus I eta mu nu over, if this is a momentum, k squared plus I epsilon. Okay. Once again, let's see if I get it right this time. So if I get an electron line or an electron positron propagator, what am I supposed to write? Actually, people don't usually denote the mass of the electron with a capital M. It's a small m. Sorry about that. It's just terminology, but it's just nice. So what do we get? We get, so if we have the momentum k, we said k slash plus m ab with an I, and then k squared minus m squared plus I epsilon. And what did we do with the indices? Well, we said, I think, we go from B to A. Okay, that looks good. How about the interaction? Well, the interaction was this object. Exactly as before. But now we get to make choices about this guy. Why do we get to make choices? Because our interaction term has a mu index, right? So we get to make choices, and therefore the interaction vertex will now be minus IE gamma mu. Of course, we could do the same thing that we did in the nucleon case, in the nucleon mesodynamics, where we had an index for this guy and an index for this guy. And we have a delta AB here. Well, in that case, we had a delta AB, and in this case, we will have the two indices that label the components of the gamma matrix. But guess what? I'm not going to write it, because nobody does. So I'm not going to be the first one to teach the whole thing with all the indices. So, but keep in mind, actually, then I shouldn't have done it here either. But in any case, so there are supposed to be two indices here corresponding to the two choices that you have here. Okay? Last but not least, we have the external particles. And here they are. Except, you can say an incoming electron, an outgoing electron, an incoming positron, an outgoing positron. Okay? And finally, an incoming photon. We will have some polarization, and for an outgoing photon. So last time we had a convention where the two polarizations, the two physical polarizations were conjugate of each other nicely. So we could just write the polarization vector for the outgoing guy. But in general, people like to distinguish the outgoing and put a complex conjugate in it. Okay, so those are the Feynman rules. I don't think there are more rules. Well, yes, there is one more rule, which we could discuss. Yes?
So before we did last theory, we had this other guy. That guy is not allowed anymore.
Which guy?
The double, that had AUA.
Oh, we don't.
We can't have it because of the isolation properties now?
Well, we just wrote down the simplest Lagrangian, right, with only marginal or relevant couplings. In fact, in this case, the coupling was only marginal. So what's the dimensionality of the coupling? What's the dimensionality of E? The dimensionality of E, well, let's just say that A has the dimensionality of a scalar field, right? The space components are like scalar fields. What's the dimensionality of a scalar field? It has dimensions of mass, right? Well, and it has the same dimensions as this guy. So if this formula is going to make any sense, what's the dimensionality of E? It's 0. So it's a relevant coupling in 4 dimensions, okay? So this is a dream Lagrangian. It's completely fine. Now, I'm very glad you asked. So now I'm so happy with the homework. You're going to see, well, it's also an optional problem. But now that you ask, maybe it's not optional for you. Now, you write it down somewhere there that for NEMA, it's not optional.
So
yes.
when we're looking at the big experiment, I can put polarizations for polarizer for polarizations, but in this case I have the extra information about the spin of the electron and the positrons, or I just have to take into account every possibility.
No, like we did for the nucleons, right? The nucleons also had, say, the nucleon was a proton. Yeah. So it also had spin up and spin down. So we could also put polarizers that select one of, I'm not sure if they are called polarizers. Yeah, you can separate, you can separate them, okay? Very good. So there are a few more rules, but let's state the rules as we use them, okay? So that would be more, I think it would be more useful, yes.
I'm always confused about the complex conjugate on the photon. Is that just convention, or can you say more about that? Because why did it basically not have?
Yeah, in the other case, we had a choice. We made a choice for the explicit polarization vectors so that the star of one polarization was identical to the other polarization, right? So we just had to declare what was the polarization of the, say, well, we're projecting out this guy, and when you project out that particular guy, that's the one you use, okay? But in general, people like to call it just to put the star. Okay, so, oh, yes, that's right. So we have few examples. Actually, there are many examples. We can do as many as we want. Let's only do 17.
Example every minute.
No, today is Friday, right? We can go on forever. Okay, example 1. Now let's be super careful with everything for once. But at least I'm going to try. Okay. So electron-electron scattering. So what do we get? Feynman diagrams. And the other one, so sometimes people like to draw it like this. It looks nice. But somehow it doesn't make justice to the fact that we're supposed to put a minus sign, or maybe. Yes, it's exactly the same diagram that we had in the previous, right over there. I just drew it in a different way, okay? It's the same as the second diagram here, but just drawn in a strange, just to look a little bit smarter. Okay, so let's use our Feynman rules for the first diagram, right? So diagram 1. So what do? Yeah, follow the fermion lines. We have 2 fermion lines, so we start with 1 fermion line, say the top one. And then what we do is to start following the fermion line, but we write from the right to the left. We say UPA SA. Now we go down to the vertex, and what do we find in the vertex? Well, in the vertex, we're going to find a gamma matrix, okay? And a factor of minus IE, which I'm going to put out. But this gamma has a vector index mu. And I'll have to figure out what to do with that vector index at some point, okay? But I don't worry about that yet. I just keep going following the fermion line until I'm done with that fermion line. So the next step is the U bar S1, K1. Now I got a number, so that looks pretty good. A number for each of these components. Okay. Now I follow the other fermion line, and I go from U, PB, SB, gamma. This one can be different, say gamma nu, U bar, K2, S2. I also have my minus I E from the coupling, and we're only missing the propagator. But that's pretty good, right? Because it's a photon. It's a photon propagator. And therefore, the photon propagator depends on these indices. And it's just what we need to actually get a number. So that's pretty good. Over PA minus K1 squared plus I epsilon. Okay. Now, same thing for the second diagram. Except we have to remember to put our minus sign. Okay? So the same rule that we had before, we have to apply it here because it's the same situation. Okay? Now, our example 2. Once again, this is an example of a single Feynman diagram. Okay? And here it is. A big circle. We have one photon coming out, another photon, another one. Guess what? Another one. And any number of them. N of them, just for fun. So one loop diagram. How about that? And these are electrons. These are fermion fields going around in the loop. So we have to give some momentum, label the momenta. So let's say that the momentum flowing here is L. Of course, this momentum is not going to be fixed by momentum conservation, right? Because there is nothing that can fix it. Once you give me the momenta of the external photons, there is nothing that tells me what this is. So what does the rule tell me? The Feynman rule tells me to do. Integrate and cross your fingers. Okay? Well, it turns out that if n is large enough, this integral is completely finite. So there is no problem. So I'm not worried about that. This is L minus K1 if you take this momentum to be outgoing. In fact, I'm going to use a convention where all momenta are outgoing. Okay? So we just get L minus K1 minus K2 and so on. And this one will be L plus Kn. Because it's also going in that direction. And this momentum is Kn. Okay? So what do we get here? Well, we get tons of interesting things, but I'm only going to worry about what happens to the fermion line. And this is something that you guys did today in the tutorial, right? For a simpler example than this. So every time you see a fermion loop, what are you supposed to write? A -1, okay? So we write a -1 for the fermion loop. And you see that when you follow the fermion line around and you close the loop, what's going to happen is that you're going to start, say, with, we can start with this propagator. Let's start here at this point. So I'm going to start at that point, and I put a gamma mu n. It has an index mu that I have to keep. And then I keep following the fermion line around. So the next thing that I'm supposed to write, and I'm going to use a super fancy way of doing it. Okay. Mu1 I over L minus K1 slash, minus M. And I keep going all the way. So let's put the minus 1 here. All the way to the last propagator, which is L plus Kn slash minus M. And the last delta function, the last vertex, logs the index of this matrix, the final index here, with the initial index here. And what's the name for that? It's called a trace. So we just take the trace of this matrix. And the great thing is that we didn't have to write a single index at all. We just treat everything as matrices. Of course, now there will be the polarizations of the photons. And the polarizations, there will be one per photon. So the indices will be contracted one per one by one. Okay? But we're not going to do it, because the whole purpose of this exercise was to show you the trace and the minus 1. So for every index loop, you will get a minus 1. Sorry, for each fermion loop, you will get a minus 1, and there will be a trace. Okay? And last, but not least, our last example is the annihilation of an electron with a positron into two photons. Okay? So what are the Feynman diagrams? We have this one. Now this is our electron line with momentum PA. This is our positron line with momentum PB. We have our polarization epsilon 2, epsilon 1 here, plus this other one, which I'm going to draw in the same way that I did there. Okay. So what do we get for this diagram? Well, once again, we start with a fermion line. We start here. We write U, PA as A. We get here, we get a gamma with some index mu, which I'm going to contract later. There must be somebody who hits that index, so I'm not going to worry. There will be the propagator, which I'm going to write again in fancy notation, because we don't have too much time. Gamma of another index, which happens with this vertex, times our incoming positron. And I look over there and I say, well, when I have an incoming positron, I'm supposed to put a V bar, SV, of momentum PB. Okay? Every vertex gave me a minus E squared, sorry, a minus IE. So I get two of those. And now I put the polarizations. Contracted with a corresponding index. So which guy goes with mu? Epsilon 1. And epsilon 2 goes with nu. Okay? So the next diagram is your exercise. But the only reason I went through this, yes?
So before you said when you follow the fermion line, follow it from the right to left.
Yes.
But in here, we're going from up, bottom to top.
No. follow the fermion line always from the beginning to the end, but when you write from right to left.
It doesn't seem like there's a beginning and an end.
Yes, this is the beginning. I follow the arrow. Yes, so, yeah, sorry, well, I had to define what the beginning is. I somehow assumed that when you see an arrow that has a direction, the beginning would be where here. Yes. No, but it's a good question. So to be completely well-defined, when you see a fermion line, start, yeah, I don't know how to say it. Start where the thing starts, somehow. I mean, you know what I mean. If you were following the line, the direction on the arrow, okay, then go all the way back to the beginning. Yes. Okay. But the reason I wrote this down was not just for your amusement. It's because part of the exercise, actually, which you should try, is that what will happen to this formula if by any reason, so what will happen if, this is something we can do in our notebooks, right? There is no problem. We can take epsilon1, star or not star, that doesn't matter. Just take epsilon1 and replace it by a real vector. Which vector I'm going to use? Just replace it by k1 mu. Okay? Just in this formula. Remove this and put k1 mu, where k1 mu is the momentum of the photon, of this photon, right? Our standard notation. So what are we supposed to get? Exactly. So what should be the probability of scattering an electron and a positron and producing one photon that has a longitudinal polarization? I mean, in fact, it's not even called a photon. It's producing a strange guy that has a longitudinal polarization. So in our theory, if we did everything correctly, and our theory makes sense, this amplitude should be 0. So that would be amusing to check. Yes?
So when we have this scattering diagrams, there's a relative sign between one and the other one. Right? Because I'm changing frames, but in this case...
Yeah, in this case, there isn't.
There is not, but I can view it like fixing the two outgoing photons and exchanging the incoming fermions, and that will give me an extra function.
No, because you're also the weight. We will have to think about when we write down I mean, to really decide the sign, we'll have to go back to the correlation functions. But you can also think about these guys, which are bosons.
Okay,
so you can flip them. Yes.
So if I follow your suggestion, the internal line would the arrow.
Okay.
Oh, that's right. That's right. So there is no symmetry. You cannot exchange the two. Yes. Oh, sorry. That's right. We don't have two identical. In this case, we have a positron and an electron. Yes. Sorry. Yes.
When you say this is 0, that's because I know it has to be 0 somehow from this end. I know it has to be 0 because we said anything along the line.
Yeah, exactly. With what we did in this course, is just pure hope.
Okay, so it
Yes.
has to be.
Well, it better be 0. Otherwise, there is something wrong with what we did. In the next course, you will prove that it's actually 0. I mean, that in general, it will be 0. But with the technology that we had in this course, we didn't prove it. Okay? Now, that brings me to precisely that question. So in this course, we have done many crazy things, right? So we went from classical field theory to quantum field theory. We met infinities. We struggled with the infinities. We said, well, we can regulate them. We can regularize them. And so right now, we should really sit down and regulate this theory using dimensional regularization, renormalize the theory and compute observables and check with experiments, okay? Of course, that would be hard to do in 10 minutes or 9 minutes, okay? So instead, let's actually describe something that people have done. So this is called Y is QED and also QFT. A reason you should be proud of being a human being. Okay, as I like to say, if aliens come to Earth and then they say, well, should we destroy you or not? I mean, show me something that shows that you're reasonably intelligent. Well, what I'm going to show you will be the thing that you have to do. Will be one of our best shots, I have to say. So recall that the potential of a scattering, this goes back to my childhood, but probably yours is actually closer than mine. But this is something that you see as an undergraduate. So recall that the potential of the scattering of an electron with a magnetic field B is, the potential is given by minus something that is called the magnetic moment of the electron. Okay. And the magnetic moment of the electron, which you should remember, is written as okay, where this is a spin operator. And this G is called, that's right, or also the G factor. And in quantum mechanics, we learned that for the electron, I mean, at least the value that everybody writes in the books is what? Is 2. Exactly. And this was the big success of Dirac's theory. The first time he came out with it, the prediction is that it's 2. Now, how do you actually go and compute this thing? Well, you do it by computing Feynman diagrams of an interaction that looks like this. You have an electron coming and interacting with our photon field. Of course, the magnetic field is nothing but a photon field. So our electron interacts with some background photon field. That's very good. And Dirac's prediction, too, comes from just doing a computation using the basic interaction that comes from Dirac's calculation. But then people made experiments and found that the answer was not quite 2. It was different from 2. Okay? within experimental errors, it was definitely not 2. But Schringer managed to catch up with the experimentalists. And that was really a big success because at the time, he had to compute something that looks like this. Which would be the next order in the same kind of interactions. And the moment you try to do something like this, you find infinities. Imagine what he felt. You find these infinities, what do? You're all confused, you don't know what to do. People said that QED was ill-defined, that nothing would make sense. But these guys just push through, and then they say, well, let's follow this procedure of regulating and regularizing and see what we get. So he did, and he found that this diagram contributes to G. So this was Schringer in 1948, not long ago. He found that this diagram contributes a factor of, it's convenient to define structure constant alpha, because after all, that's what's going to happen as the perturbation expansion parameter, because every time you put a photon line here, you will have to touch it twice, so you will get 2 powers of E. So every order that you increase, your calculation will pick up a factor of E squared. So he found that the answer was this. That diagram contributes that number. Okay? And then this number matches what the experimentalists could measure. That was great. Now experimentalists kept going and making better and better experiments and found something that disagrees with this. You say, well, what happens? Well, this is not the end of the story. This is just the first subleading interaction. Now you have to keep going, okay? Very good. So nowadays, people like to define the anomalous magnetic moment as G minus 2 over 2, okay? The true G, I mean the correct G that you measure, minus 2 divided by 2. And then, of course, Schringer found that this thing was 1/2 alpha over pi, okay? Note that this is a very small contribution. This thing is 0.0011614, and so on. So it's a very tiny correction, but the experimentalists were able to actually fix that and measure it and realize that it's not the correct answer. You still have something that is different from that. Okay? So we could go on and on and on about the story of experimentalists beating theories and then theories beating experimentalists, okay? But let me just tell you the summary. The summary is that as of 2010, which I found in a talk by one of the heroes of these calculations, actually one of the very few people in the world who knows what's going on, Yoshiro Kinoshita. Okay, so he gave a talk. You can find it online. It's a talk at a place called Riken in 2010. So what I found there was a very amusing summary of what's happening. So you have the calculation done by Schringer, calculating one Feynman diagram. Okay? Now, we know this is not the right answer because experimentalists beat us, so we have to go to the next order. So they found minus 0.328 alpha over pi squared as the next correction. And guess what? You have to compute 7 diagrams. Okay? Then you keep going. Experimentalists measure it, and then they again beat you. And then you go to 1.11 son alpha over pi cubed. And guess what? 72 Feynman diagrams. have to be computed. And you go here.
This is just an ego battle.
No, it's not, because the moment you find a discrepancy, you find new physics. It's a desperate race for new physics, really. Of course, you don't tell that to the aliens. You say, look what we have done. 891 Feynman diagrams. Okay? And what do you get? Well, when you look at this thing, and you add them up, you get that the anomalous magnetic moment calculated from QED is, and I'm going to use units of 10 to the minus 12. Okay? So you find that the anomalous magnetic moment for the electron is 1,100,000,000, well, in these units, right? So remember that Stringer's number here was 1 point, in these units, it would be 1,1614, and so on, computed from here, times 10 to the minus 12. So it would be 159,152,182.79. And the reason we put this horrendous number here is that we want to quote the error as 7.7. Okay, that's the error. Well, here comes the test. And this is the thing you should really tell. Well, experimentalists, the theoretical error. Well, first of all, the error that you estimate from diagrams that you haven't computed, and also estimates from, yeah, that would be a little bit complicated to explain, but yes. Yeah, these are errors. This is the error in alpha. That's right. Actually, the error from the diagrams you haven't computed is of the order 1, while the error from the measurement of alpha is mainly that contribution. It's experimentalist fault, yes. It could get better, yes.
Is this a theoretical number to fourth order in alpha, or is somebody going past it?
No, this is fourth order in alpha. This is this answer. I'm writing this answer. Okay? So, yes, well, in 2010. Okay. So here we go. So this is in 2010, this is the state of the art of experimentalists. We get 159,652, 180.73, 0.28 times 10 to the minus 2. Okay? So that's the reason why we study quantum field theory. Because it's just correct. I mean, mathematicians might not like it, but it's correct. So there is no questions about it. And besides, anything that you want to modify in anywhere in the discussion we had in this course will have to be such that you don't mess with this agreement. So that's going to be a challenge. Okay, so let's end the course here.